Today we are walking through the paper titled There Will Be a Scientific Theory of Deep Learning.
Is this paper proposing a new model, or is it making a bigger claim about deep learning?
It is making a bigger claim. The authors argue that deep learning is starting to admit a scientific theory, one that predicts training dynamics, hidden representations, final weights, and performance.
What name do they give to that kind of theory?
They call it learning mechanics. The analogy is to classical or statistical mechanics. Instead of tracking every microscopic detail, the theory should explain the macroscopic quantities that matter during learning.
Why do they think older theory has not already solved this?
The gap is scale and complexity. Modern systems can have hundreds of billions of parameters and many interacting components, so a microscopic account of every weight is not practical. The paper also says current nonlinear toy models capture useful slices of learning, but no unified framework has emerged for models that are nonlinear in both the data and the parameters.
So what is their proposed route forward?
They organize the route around 5 bodies of evidence: solvable idealized settings, tractable limits, simple empirical laws, theories of hyperparadigms, and universal behavior across systems. First, let us look at the method-style evidence linearization. One route removes nonlinearities from the architecture, making the model linear in inputs, while the parameters still interact nonlinearly.
So this simplified model is still useful because the training parameters can behave nonlinearly.
Exactly. Deep linear networks are simple enough to solve in many settings, but they still expose non-trivial learning dynamics in the weights. The second route linearizes around the initial parameters. That gives a model that is linear in parameters.
What does that trade off against the deep linear case?
It flips what is simplified. The data side can remain nonlinear, but the parameter dynamics are approximated, near initial homogeneous. That is why the paper treats both views as useful but incomplete. Equation 1 is the deep linear network written out. It defines the prediction as a chain of linear transformations applied to the input.
What are the important pieces in that equation?
The input is multiplied by a stack of matrices. Each layer is linear, but the product of many trainable matrices makes optimization non-trivial, so the equation isolates weight dynamics without activation nonlinearities. Equation 2 is the linearized network. It keeps the model value at initial homogeneous and adds the first-order change caused by moving the parameters.
Why introduce that approximation?
It makes training analyzable near the starting point. The gradient term says how the output changes when parameters move, so the paper can compare rich feature learning against lazy behavior near initial homogeneous. This figure makes that lazy versus rich contrast concrete. With a small output multiplier, student weights grow and cluster around teacher feature directions. With a large multiplier, the loss drops but the weights barely move.
So the comparison is not only final loss, but whether the representation changes during training.
Right. The paper uses this as evidence that learning mechanics should predict trajectories, not just endpoints. Two trainings can both reduce loss, while producing very different movement in feature space. The next evidence strand is scaling loss. The paper points to empirical laws where loss changes predictably with compute datasets eyes or parameter count.
What makes scaling loss count as evidence for a theory?
They are coarse, quantitative, and testable. A-bar law does not explain every internal mechanism, but it predicts a macroscopic observable how loss changes when scale changes. The paper also highlights the edge of stability. Even though the full loss landscape looks extremely complicated, training can show repeatable coarse behavior near stability boundaries.
How does the paper connect this to hyperparadigms?
It argues that some hyperparadigms can be disentangled from the rest of training. If learning rate, width depth, and architecture choices can be put into controlled limits, the remaining system becomes simpler to study.
Does the paper claim those limits always improve performance?
No. The discretization hypothesis says finite-size corrections usually worsen performance while saving data, time, memory, or compute. A finite-size benefit that cannot be achieved in the limit would challenge that view. Another result-style claim is universality. The authors point to cases where large models train from different seeds, and sometimes different widths, architectures, data, or objectives, learn similar internal representations.
Why is that important for mechanistic interpretability?
Interpretability often assumes that meaningful features correspond to directions, circuits, or localized components. Learning mechanics could formalize when those assumptions hold and explain how such mechanisms develop during training.
What are the strongest limitations the paper admits?
The paper is explicit that the theory is not complete. Open problems include solvable nonlinear models, a theory of natural data, precise definitions of learned features, and a better account of implicit simplicity bias.
So what should a viewer take away from the whole paper?
The takeaway is that deep learning theory may be moving from isolated explanations toward a mechanics of learning, a quantitative science of training processes, representations, and performance.
That helps. The paper is not saying the theory is finished, but that enough regulatories now exist to make the project concrete.
Exactly.